But that's similar to what we're doing right now. So we're building our way up towards the hydrogen atom. That means we have to understand rotation. Now, here's the kick. I just want to drop a couple of hints here. The number one thing is that, and don't write this down, but the Hamiltonian you have been dealing with is of some constants, and that's not hard, but this. Okay, this is, all right, this is planar, right? So this works when everything's flat or moving in a straight line. Electrons move in a circle. So you can't do this anymore. You've got to work with R, theta, and phi. So the ultimate goal here is everything is always in the kinetic energy operator. The kinetic energy operator is always the hard part of quantum mechanics. So instead of double derivative in x, y, and z, it's now got to be r, theta, phi. So maybe not write that down. I didn't. We're doing that. This is like literally what we're doing today. So again, the problem is that the electrons in the hydrogen atom are turning in a circle, and if you're moving, you have kinetic energy. It's just a rotational kinetic energy. So I'm even going to cover some of your physics mechanics, the physics of rotation, because it's just good to. I'm guessing you may have forgotten all that. Even though I teach this class like every other year or so, I will have forgotten all of this before I teach the class again, so I'm guessing you have as well. Also, here's another thing I wanted to mention, and I'm going to talk a little bit about this today or maybe Friday. Light, does light have angular momentum? Who remembers the very first problem set? Or second one, does light have angular momentum?
Yes.
Right, so it's rotating. So the thing is that spectroscopy, which is quantum mechanics, is really mostly good for spectroscopy. It shows that there are discrete energy levels, and when things absorb light, they're going from like the ground state to the first excited state. Well, the thing is that rotation is automatically a part of that because light is rotating. So not only are things round the fact that things are round make all this quantum difficult, atoms are round, light is also simultaneously rotating, and you really only do this for spectroscopy, which is just an extra kick in the pants. Okay, anyway, so let's start out easy as humanly possible. So what we're going to do is rotation, 2D rotation. Okay, so we're going to start at 2D rotation, mostly finish that today, and then Friday, the double lecture. That is such bad timing. I can't emphasize that enough. Such bad timing. Both those lectures back to back. We're going to get the 3D rotation on Friday. Okay, so rotation, 2D rotation will just be in a plane. And to get you calibrated to how this works, let's just have, so we're going to work, I'm going to tilt things to give it kind of a 3D effect, but we'll just call this like X and Y. So what you've done is you've got a little pin in a plane. Now again, remember, I'm going to try to like tilt things a little bit to give it a very 3D-ish look. I've got to do all the, and no, this post has to be, no, that's wrong, isn't it? So one reason I covered particle in a multi-dimensional box, and I started introducing multi-dimensions is, as soon as I talk about rotation, I can no longer just be in the X-plane, right? I'm already multi-dimensional. 2D is just just two dimensions. So what's happening is that the particle's like on a string, and of course it's just rotating around the string. So it's confined in the XY plane. This is way easier, right? When we get to 3 dimensions, it's not like it's just the same thing now with the Z. That's not going to happen at all. It's going to even get way more complicated than what you're going to see today. Today, and also heads up, a lot of the derivations we do today will start out pretty badly complicated, but they'll narrow down to something simple, like almost everything you've seen. 3D does not do that. It starts out complicated and then actually it grows. It does the opposite. I know you've seen this a zillion times. I start with a complicated equation. Oh, and look at that, after solving some integrals, it's just a pi or something. And then everything's very easy. The exact opposite happens in rotation. It actually expands. Not so much with 2D, but with 3D. I shouldn't really be saying all this, but anyway. Okay, so XY plane, things are rotating. First solve, as also you're hopefully used to, first solve wave functions, make sure they work in the Schrodinger equation, and then see what else you can get from that. Okay, so 2D rotation, the wave functions, it's about half free wave, and that's because we don't have a potential. We'll do this with no potential energy. So what I've done is I've made this a flat plane, right? So there's no hills. It's not like trying to roll around a track that's going up and down, right? So that means no potential. Okay, so what's the other half is particle in a box. Okay, so the solutions, wave functions, the energies, the properties are, you always see one property of a free wave and one property in the particle in a box. Now, the free wave is the fact that there's no potential, and by the way, the wave functions are like e to the ikx, so that's where you see that. The particle in the box actually comes from this. So the wave function has to be in this track. It is kind of funky, but let's think about this. These are like particles, and I drew this up here in case you have trouble seeing or if the camera doesn't really catch. Yeah, I've done this about, no, that's about the same. I guess I had this upside down. Anyway, okay. Now, a particle in a box says, okay, so let's say that there's a box here. These aren't quite, maybe it's like this. Maybe these aren't quite the right wave functions, but regardless, the point is that if it's going to follow a track, we fold it over, and now you have to see whether you're going to satisfy the usual this or that. Is it smooth? Is it continuous? And of course, it's the seam that seems to matter. And you can see the flat line. The flat line is smooth and continuous, the one on top. The half curve it's got a problem. It's got a cusp, and that's bad. That doesn't work because that requires infinite energy. And the full wavelength actually is okay. You can see that it's smooth and continuous. And let me just look at that. I just want to get you, and I mostly just show you this so you know what I'm drawing here. Okay, so again, the particle in a box, it has a boundary condition because it has to bite its own tail. So the box, the wave functions have to be 0 at the endpoints. Here, you have a boundary condition. It's a smooth and continuous boundary condition, and that is that it has to start where it finished, and be smooth at the same time. So that's smooth and continuous. Okay, so this guy's okay. This guy fails. This guy's okay. So you can see what I'm doing is I'm trying to figure out a way to translate particle in a box into rotation, and what I can do is I can eliminate the, this was our ground state in the particle in a box, and now I can't use it. I can't use it for rotation. Our first excited state's okay. So anyway, all right. Next thing, when I'm trying to solve wave functions, usually what I do is I want to solve the de Broglie wavelength, because the wave function has to incorporate the de Broglie wavelength, and then I have to make sure I understand the Hamiltonian, which is supposed to be able to draw out the de Broglie wavelength. Question?
I wanted to make sure I understand. We're not actually rotating the plane that thing's in?
No, just exactly what I did here.
We're just spinning the surface.
It's exactly what I'm doing right here. Okay. Now, as for what is an accurate description of what I just did, it's up to you, but just remember this. Right, so rotating. Remember, the wave function is following a track. So maybe in that drawing I just did, so let me again give it a little tilt so that it's kind of fancy looking. So it's following this track. So it would have to look something like this. Oh, I'm drawing that all screwed up. But anyway, so this is the idea. Okay, now let's figure out the wavelengths, right? Because there has to be a wavelength, and then it's got to be a de Broglie wavelength. Okay, what's the wavelength of this one, of a flat line? Now I know that this is not technically a particle in a box. That's a particle in a box with no kinetic energy. And that's not normally allowed because a particle in a box has to have some kinetic energy. This is where we're going to find one deviation. This is a deviation from the particle in a box behavior. This is more free wave behavior. Free wave kinetic energies can be arbitrarily low. Basically, they can be 0. It doesn't really correspond to anything, but free waves can have no kinetic energy, and this is one of them. So this is where it's more like a free wave. What's the wavelength? Okay, tell you what, if this is, all right, that's a wavelength, right?
Mm-hmm.
How do I turn this into that?
Infinite.
Right, stretch it. Stretch it out to infinity. Okay, the wavelength is infinity. Okay, now this guy we're going to forget, and this guy, we'll tell you what. Let me. What is the wavelength regardless? So we're forgetting this one, but what's the wavelength? We can solve it because there's a pattern. What's the wavelength of this one? Sorry. Here, it helps if I give you a length scale, right?
Over 2.
It's
2L.
2L, right. The wavelength is 2L. Now remember, we're actually crossing that out, so don't forget that. And this guy's wavelength is L. Okay, now let me express this in a way that shows you what the pattern is, and then you can figure out like ground state, first excited state, and you can figure out all that jazz. I'm looking for the quantum number, by the way. Remember that the quantum number delineates ground state, first excited state, second excited state. It almost always is the thing that counts nodes. No nodes is the ground state. Usually n equals 1, nu equals 0 for vibration because that one's weird. Okay, so I'm looking for the quantum number that tells me the number of nodes. Okay, so now I like 2L because of this guy here. So 2L, now how do I turn 2L into infinity? What would I divide it by?
0.
Yeah, there we go. Okay, this is the wavelength. So what I would do is I'd take 2L and divide by 1, and then I would take 2L and divide by 2. See the pattern? 0, 1, 2. Guess what the next one is?
2L over 3.
Right, but it wouldn't be allowed. Then the next one's 2L over 4. Right, because the next one, of course, will have a node. I can't draw. You can see my drawing. I do the best I can, but sometimes I'm not so good at it. Okay, so what I can see here, I can see the pattern already, the recursion, and what it is the wavelength is L over M, where M is 0, 1, 2, ... So I took out the 2 as well. So, right, so let's see. Okay, that one's there. Then I've got this one, then I've got L, and then the next one is a half L. So, right, it has the right pattern, so that works. So don't get confused that the 2 goes away. The reason the 2 goes away, right, I have 2L here, but I don't here, is because every other one is actually not allowed. That's why the 2 goes away. Here's another thing. Now I wish I hadn't, I keep drawing this and then I have to draw it back. Okay, so if this is plus M, let's say that's plus 1M. Am I missing something? Spin, kitty.
Spinning in the opposite direction?
Yeah, you can spin the opposite direction, right. There's 2 ways to do this.
So aim is plus minus.
Right, so you can do this. ... Okay, so again, remember how many times I told you this and you're probably sick of it? You figure out wave functions and you never use the Schrodinger equation. We actually have to derive the Hamiltonian, by the way, just like we're deriving the wave functions first. Then we'll derive the Hamiltonian, which is the thing we're supposed to solve to find the wave functions. Not that we're not finding them now. Great. Anyway, so there you go. So now we have the de Broglie wavelengths, and now we just got to start trying to figure out how to incorporate them into the wave function. Now to do that, I want to do some more simplifications because 0 to L doesn't make sense on a round track. What should I be using? Right, R. Okay, and L, of course, is 2 pi r. Okay, so therefore, the wavelength is 2 pi r over M. Also be careful, this is also a sucky thing. Notice that I've got another M. M is now a quantum number. It used to be mass, now it's quantum number. So from now on till the end of class, I write the word mass for mass. M is the quantum number for rotation. Sorry, just right, there's only so many letters. I We need to just use more of the Greek alphabet, but it's traditional. If I don't show you this way, then I may see it another way on like a standardized test and then you get screwed over. So just be careful of that. I know that's a little sucky, but there you go. Okay, now I've been talking about momentum, from the de Broglie relationship, and of course that is h over lambda, and so now I know what that is. That is mh over 2 pi r, and as we see over and over and over again, in quantum mechanics, whenever you're dealing with anything really, anytime h shows up, and it always shows up in momentum, a 2 pi is somewhere. You will never not find the 2 pi. And so that's why h bar was defined as a fundamental constant, because it was just easier in every quantum mechanical relationship you'll ever find. Back in the 1935, they just said, oh, let's just start calling it h bar, because otherwise we're going to have h over 2 pi in every single equation we ever derive. So anyway, I mentioned that before. So, but you're just seeing it again. You never avoid that. I always thought that was kind of funny. Okay, energy. I'll just keep working down, and then we get where it gets kind of difficult. So now that I got momentum, energy, of course, is momentum squared over. Okay, hold on. I have to think about this, and now I have to start worrying about mass. Okay, that is momentum squared. Momentum squared over 2 times the mass. Okay, which is, of course, m squared, h bar squared, 2 times the mass times r squared. Okay. Yeah, there we go. Now, one thing I'd like to do is we'd like to call, any of you recognize, let me remind myself, mass times r squared. Now I'm going to review your mechanics, your physics, right? You had mechanics in physics 1 and E and M in physics 2, right? Okay, that's kind of traditional. That's how we covered it. When I have a mass at the end of a string, does that look familiar? Mass times r squared? You may have forgotten. Did you do this with freshman or sophomore year? Yeah, I was kind of nerdy too, so I ended up in my freshman year. This is called moment. Right. My spelling is bad today. Right, moment of inertia, which is given the letter I. Just right. It's just more symbols. You know, one reason we do that is that I won't have to write mass nearly as much. I can just write I, and so you won't get confused about the M. So again, look out for that. Now, when it comes to rotation, rotational energy, you may have also remembered it as angular momentum squared over 2I. And so that was J squared over 2I. And where, J is angular momentum. And again, I'm going to review like literally in 30 seconds. What's nice about this is that this now looks like J squared over, it looks just like what we had before for kinetic energy in a straight line, P squared over 2M. It looks like P squared over 2M, but it's not, right? Because it's not. It's J squared over 2I. So again, momentum P is now J because it's rotating, and then I is I because it has to take into account the track that it's following. Of course, the momentum of inertia is bigger if the thing is rotating out on a longer string and whatnot. And you all know the dancer pirouette. They fold in their arms, and you had all that in your freshmen. Now remember though that J. The reason that J is not P is that it's R cross P. You remember that? It's been a while. Let me just remind you of that because, again, it's something I forget. And again, I'm going to be tilting my axes to make it try to look fancy. Okay, here's Z, not Z squared. That doesn't make sense. Vector Z. I'll have X like this. And the little hat just means it's a vector. There's nothing special about that. And here's Y. Now, the reason I really wanted to put this in a 3D sense, because there's something, here, let me go in a plane and then let me go back to 3 dimensions. So, okay, so here's my little object, and it's rotating along a track. And, I'll stop it right here. So of course, it's got it's attached to a string of length R. Okay, so just want to remind you that. So, so R, of course, is a vector. God, I'm writing really small. I don't know what's wrong with me today. So R is kind of small. What's the momentum? Now again, so I'm letting it rotate. I've stopped it here to analyze it. So when you're stringing, you let go. It just goes outward, right? You used to run a nuclear power plant. You're swinging, and let's say it's coming at you, and I let go. It goes that way.
No,
Right. It continues that way straight. Remember how when you're a little kid, you're always fooled because when you're riding a merry-go-round, you feel like you're being flung outward, but you're just really being flung forward. You get confused because you're simultaneously turning. Right, so P is in this direction, just like I drew it. So, oh, that's really a vector, right? Sorry, I should draw these like this. These hats mean directions, and the little half arrows mean are vectors. And so what about that? Remember that now you have learned this a while, it's been quite some time, that the angular momentum is R cross P. Right, remember, it's a cross product. Now what's cool about angular momentum, the purpose of it is that, I just kind of want to, this is just to recalibrate you on what R and P are, and that this is angular momentum. This does a lot for you. It's very helpful to think of rotations. Instead of 2 vectors, the cross product is a single vector. And when something is rotating, and I have to be very careful about this, so I'm going to work across from this. So I'm still in the same plane. Here is the J vector. It looks like I drew it a little bit off, a little bit of a tilt. So there's J, there's the J vector. And given that we're in the XY plane, you can just say it's entirely in the Z direction. Don't worry about that for now. It'll come up in Friday when we do 3 dimensions. So you see what you've done is you have taken a 2-dimensional thing and turned it to 1. Now, how did I know to draw it up? Right now, why didn't I just do this? We're going to draw a little track. Sorry, it's not, yeah, it's kind of ugly how I'm doing this. But why not down?
You use the right hand rule.
Yeah, you guys remember that right hand rule?
Spin your right hand fingers in the direction of rotation, and your
thumb points in the right direction, right? So here it points down because I'm rotating the other way. Right? You remember this? I think there's some. If you learn some electronics, there's like another rule.
Tons of right hand fingers.
Yeah, for all this jazz. So okay, so I do want to point out though. So what's nice about this is that it conveys a lot of information. It conveys 2-dimensional information with 1 dimension, which is just convenient, way convenient. But you do lose a little bit, which is that if you recall the definition of a cross product, you get the length of the vector, and you've got 2 of them, R and P, and then you've got the sine of the angle between them. And then you've got to also put that in orthonormal, so N means normal direction. Now, of course, anything rotating in 2 dimensions, one reason I like to do it this way is I want to remind, I should have done it, anyway. Whenever anything is rotating, however it rotates, you can always take your coordinate system, like your head, and just turn it. So you can always make anything rotating in a plane, you can always define that plane as X and Y, and then the normal direction is automatically Z. Anyway, I'm just being very formal there. Now another thing is, let's see. All right, let me just continue this way and remind you about, so one thing to appreciate is while we're doing 2D, everything will be in the XY plane, and all the energy and all the momentum's moving in the z direction, and still energy is j squared over 2I. In classical mechanics and in quantum mechanics, it ends up being the same thing. And this is one of the few times that you can kind of bridge the classical and the quantum without too much difficulty. So let's see, how do I want to do that? So if the normal direction is z, then sine of the angle, of course, is just 1. And let's see, so j, which is now the z direction, and don't worry so much about that, not now. So that's r, let's just make, that's just the length of the vector. The momentum is, we've already covered it, mh bar over r, so that's mh bar. Again, where m is a quantum number. Energy is still j squared, jz squared over 2I, which ends up being m squared, z squared, m squared, h bar squared over 2I. So, which is what I erased. Great. Anyway, so there you go. Now, the reason that this worked out so well, of course, is because I inserted, so you know, if this seems like I'm kind of trying to trick you here a little bit on purpose, I'm reminding you of your classical mechanics, and then I still derived the quantum mechanical answer that I stupidly erased. But how could I not when I inserted the quantum mechanical momentum? So that's why this trickery seemed to have worked. Sometimes, as I mentioned to you, sometimes classical mechanics, what you had in mostly physics 1, and quantum, sometimes they agree and sometimes they don't. So this is one that they kind of agree in, and that will also never happen again. Okay, so the next thing is to cover, oh God, not this part. Oh, sorry, I shouldn't say that. Okay, so now we have to derive the Hamiltonian. Okay, so now you've kind of got an idea of what's the de Broglie wavelength, what's the energies. Okay, yeah, I remember angular momentum. We'll be doing angular momentum in z. Now I'm going to derive the Hamiltonian. Then I'm just going to show the wave function. Oh, by the way, the wave function is just e to the I angle. So an angle now is, instead of x, we have angle like theta. So it's e to the I theta. So the wave functions are easy. I'll just go ahead and tell you. So that part's going to be easy. That's like a free wave, like e to the I x, e to the I theta is what you have in rotation. So that part's easy. I'm going to formally derive the Hamiltonian, and then I'm just going to show you that e to the I theta is, or c, or whichever angle we're using. I don't even remember. Oh, we're using phi. Okay, so to show the wave functions work, of course I have to get to the Hamiltonian, and as I warned you, now I have to turn the kinetic energy operator into r theta and phi, and we're working in cylindrical chords. I don't know why my handwriting's so bad. Cylindrical today, we're going to do full rotation tomorrow. Cylindrical is just way easier, so we got x, y, and z goes to r. Actually, it's phi, yeah, phi and z. But z is always 0. Everything is rotating in the z plane, so you never have to worry about z. So again, this is why this part is actually going to be a little bit easier. And let me remind you, again, my attempt at drawing 3D type things, x, y, and z. What am I doing here? Oh, okay, so I've got something rotating in this plane, and this angle will be, it needs to be symmetric or the world will blow up. There we go. Okay, so that angle is phi. So remember, there's nothing happening. I hopefully drew that as well as I could. So that angle is being swept out. That's the phi angle. And if you recall, when we get to 3D, because we're doing that on Friday, do you remember what this one? Right, that's theta. So don't forget phi. Phi goes from 0 to 2 pi, and theta. Once we get to theta on Friday, that goes from 0 to pi. Don't forget that. That'll come up when we have to integrate things. Hopefully, we'll quickly remember that. Okay, so with this, I'm going to leave this up here, and now we got to start remembering how to convert x, y, z to r theta phi, because here's the damnedest thing. The big picture moment. What's happening is that Schrodinger figured out how to get the de Broglie wavelength out of a wave function by developing the kinetic energy operator. And all of quantum mechanics is difficult. All of the action is in the kinetic energy operator. And again, it draws out the de Broglie wave length. And it does that by a simple double derivative. And you just go from there, just like, like we've been doing. Now you've got to do it in spherical coordinates. So anyway, so let's, let me remind you of all of this here. I'm going to rotate what I just did back into a normal representation. So let's take the vector r, and here it makes angle phi. So there we go. And yeah, so the length will be x. The height is y. The length is x. And r is the hypotenuse. Remember that. So remember that sine is the opposite over the hypotenuse. So that's y over r. And cosine, of course, is the other guy. So that's x over r. And so therefore, things like x is r cos phi. Sorry, what's wrong with the r cos phi? Okay, so not too hard. And the one that gets a little bit more painful is, let's see, y. Y, of course, is r sine phi. And what else am I doing? Oh, yeah, this is the one that's a bit of a pain. Tangent of an angle is far over near, so that's y over x. Okay, and then the last one that is, no, we got them all. So I've got the angle defined. I've got the angle defined three ways, and I've got a way to solve. Oh, yeah. What am I doing? R, of course, is square root. That's what I was doing. X squared plus y squared. That one is so obvious, right? That's like 5th grade. You knew that. Okay. All right. I know it looks familiar, right? Not too bad. So now we're done, right? Okay. I am not trying to turn x, y into r and phi. That is not the point. What I'm trying to do is this. I'm trying to turn that into r and phi. Change in r, change in phi. How do I do that? Do I just give yourself some space? Maybe it's just, well, I have an r, and I have a phi. So there we go. There we go. We're done. What do you think?
Top notch.
What's that?
Top notch.
Yeah, no. Any ideas? You probably, there's no way, you probably don't know this, so I'm just kind of curious to see if anybody, any ideas what to do? Yeah, what do you think? What?
Start taking the derivatives.
They did a what?
A Jacobian?
Well, chain rule. It's actually a chain rule. So what you do is you make it still equal to 1 over, it's like 1 over the derivative, basically, right? So, you see it cancels. Let me check my notes, make sure I'm right. Yeah, there we go. Right. So remember how long I was telling you can treat partials like juggling, like A over B over C is anyway, right? So you can do stuff like that. So of course this guy is also, yeah, there you go. So it's like chain rule and product rule because F is a function, X is a function of R and phi, so you end up with like a product rule, you end up with 2 terms. And then I think it's the chain, I'm probably getting up the descriptions wrong, but I think chain rule is why this works, because you just cancel out the change in R's and the change in phis. So there you go. Okay, so now all you have to do is figure out what these are. All you gotta do is figure out what those are. Okay, now let me point out that the change that R, when it comes to the change in R, this one's the easiest one to work on first, is basically like the change in f of x to the half over the change in x. Now, the reason I'm saying that is I've got a function with x in it, and I've taken the square root. I don't have to solve it this way, it's just a little bit easier to follow if I do it this way, and you know what I end up with is, so this is, let me make sure I wrote that down right. Times the derivative of the inside. Right, that's still the function, that's the derivative of the inside. So you remember that notation, right? Okay, so now I just have to apply this to r is square root of x squared plus y squared. So I've got x squared plus y squared. Now it's just on the bottom, which looks like it's kind of sucky, except that's actually just r. On the top, I've got 2x. Okay, now here's another big picture. It's like, oh, okay, so that's here. No, because you can't, the point is to turn this to cylindrical coordinates. This is still an xy coordinate, so this is like absolutely what you don't want, because it still has an x and a y in it. The whole point of this is to get rid of the x's and y's. Okay, now, so the point here is, this is easy, we actually just simplify it. Okay, the 2 over 2, that one's easy. What is the square root of x squared plus y squared in cylindrical coordinates?
R.
There we go, r. Make sure, yeah, it's just r. Okay, what's x?
R cosine theta.
Yeah, r cosine theta.
So you're just not
Or cosine phi, sorry. So you just look at cos of the angle. There you go. Okay, next one. Next one. Let's do the phi dx. And this ends up being the change in a tan. So we have to look here. You can actually do this a couple of ways, but so we got to do a. Wait, did I say tangent? It's arc tangent, right? Arc tangent. Sorry about that. It's the change in a tan y over x. Or wait a minute. No,
That's amazing.
it's tangent, right? Yeah, it's tangent. Okay, I may have some. Maybe my notes are wrong. Let me just double check that. I have to check that after class. Sorry, I've been doing this for a while, so it'd be kind of stupid that I just now discovered a mistake in my notes. But it looks like, yeah, maybe I did that. So anyway, I'll have to double check that. So what I did was.
Wait, shouldn't that be, they shouldn't have wanted to go the arc tangent on the right side? Like the right side, just there? Right hand. Yeah.
That one should be on.
That should be arc tangent.
Why is that?
Because
Because if
theta
you
is
saw-
arctan of y of x.
Oh, right. Yeah, I see. Right. Oh, they have a grant, dude. Just I'm out of it. Sorry about that. Right, because tan is this, but I'm trying to get not tangent. And it would also help if I wrote down the guide. Bad day. Sorry about that. I'm gonna fix that on the video. No one will know what I'm talking about. Anyway, okay, it makes sense, right? So make sure I write the right angle all the time. And right, I define the tangent of the angle, so I have to use the arctan of that expression, of this expression to equal the angle. So that makes sense. Now, I have no idea what the heck this is, so I just Googled it because what the hell, right? And this ends up being minus y over x squared plus y squared. Okay, now what would I do with that? Y is, remember, the point is you have to turn this into spherical. We can't have x's and y's.
negative R sine theta.
Yeah, r sine. Yeah, again, I forgot the angle, and then this is r squared. So what you end up with is minus r times the sine of the angle. Over. God, it's like a Friday. Sorry, there you go. Okay, so therefore this is now equal to cos of the angle dr minus sine of the angle over r change with respect to the angle. Okay, so that's the change in x. Now, okay, so now I'm ready to write the Hamiltonian, right? Y,
You asked.
double derivative. This is the single derivative. Took about 5 minutes, right? Now, who's looked at their homework? Guess what you're doing? Yeah, you're doing the double derivative because it would take an hour. So I thought I'd just have you do it on your homework. I do. By the way, it is so long to do that I actually, on your homework, so you know that what you're looking at, I actually do the derivation, but I leave holes in it. And I have you fill in the holes to make you comfortable. Because if you want, even on a homework, having you do that derivation is too much. So I did it for you, mostly, and just left holes in it, and you just fill in the holes. Kind of. You'll see what I mean. You actually just have to do it. Okay, so what ends up happening is, oh, by the way, the way it works is, just to calibrate you, because like I say, every time I forget this, the way it works is you've got this. In some ways, it's actually kind of easy. You just square the term, right? So you square the thing. I don't know why I just did that. Minus sign. Now, let me show you where it's going to be, why you run into such difficulty. When you FOIL this, you have to, in quantum, you should be used to this by now. You have to be insanely careful about the order, right? So you know that you've got a cross term by the inner outer. So this one, and this one. Are those the same? So here, let's write it. Cos DDR minus sine. Okay, so that's one of the weird terms. And then let's do this one, minus sine. I'm not writing the angles, just I say minus sine over r d phi cos. Are those the same? Yeah, you see, yeah?
Are you saying that the double derivative is the same as the single derivative squared?
Yeah, that is. I mean, hold on. What's this? What's that? It's the double derivative, right? Apply it to a single function. It's this. So I wrote the same thing twice. Now you're thinking like it's got to be more difficult than that. Well, yes, it is. And my point is that again, you have to be careful about the order of things, and because of that, you actually have 4 terms to solve, right? And you've been thinking like, oh well, this is the square, this is a squared, this is b squared, and then there's 2ac. No, there's not. There's actually 4 terms, because I've done the odd terms, right? The inner, outer, and inner, and vice versa. Notice that, you see why there's going to be a difference? You always start from right to left. Okay, a simple derivative, whatever, that doesn't sound too bad. It's when you run into this one. It's when you run into this one. You see you're going to have some function, 1 over r ddr, and here you've got some function cosine derivative of the angle. They're fundamentally different. So, anyway, that's your homework. That's how you do double derivative of x. And then you do double derivative of y. And here, I'll just write that down, and then I know we're done. Let me just point that out. When you have finished your homework, this is what you will have figured out. Huh? Anyway, guys. Okay, so this is what you end up with. Okay, so anyway, so that's the end result, and then of course, you know, we apply this to a wave function, and there you go. Okay, so next time this will be our starting point. You can actually simplify this quite a bit, and so then we'll do wave functions. And remember, we're only doing 2-dimensional cylindrical coordinates, and then we'll go ahead and start into 3 dimensions. The three-dimensional derivation of this when I add x plus y plus z is so hard we're not even going to attempt it. We're going to write down the answer. All right, everyone.